Hello children, welcome back. Once again, chapter Thermodynamics, chapter 12, quick revision. We begin with zeroth law of thermodynamics. Zeroth law of thermodynamics defines the concept of temperature, that heat energy can only flow from higher temperature to lower temperature. And the direction of heat flow is in the direction of lowering temperature. If two systems separately in thermal equilibrium with a third system, they are also in thermal equilibrium with each other after a long time. When steady state has been reached, there is no further exchange of heat. Therefore, the system is in thermal equilibrium. The system will be at same temperature. In thermal equilibrium, temperature does not change. Two systems separately in thermal equilibrium with the third system are also in thermal equilibrium with each other. That is zeroth law statement. Okay, let us recall whatever we have learned there. You have a box containing ideal gas having three compartments. The compartments may be A and B. The third one is C. And the partition between A and B is a non-conducting one, means an adiabatic one. Adiabatic. That partition is an adiabatic condition. Partition. Of course, the surrounding partition is also adiabatic. Adiabatic means non-conducting, insulating, no heat transfer. Now the other partition here, connecting with the C, is a conducting one. A conducting partition is a diathermic partition. Diathermic. Initially, to begin with, at T equal to 0, temperature of A, B and C are not same. Let that be TA. Okay, let that be TA greater, TB greater, TC. Okay. As time goes, there won't be any direct heat exchange between A and B, but there would be a heat exchange between A and C and B and C. As I have mentioned here, at T equal to 0, say A is at a higher temperature, so heat energy flows from A to C and also from B to C. That's the direction of heat flow. And a stage comes at T equal to infinity. All those temperatures TA equal to TB equal to TC is established. This is the case of thermal equilibrium. So two systems in separately thermal equilibrium A and B with the third system C. They are also naturally would be in thermal equilibrium with each other after a long time. That's the zeroth law. So we have dealt with two types of partitions, adiabatic as well as diathermic. Diathermic partition is a conducting one, adiabatic one is a non-conducting one. Adiabatic partition does not allow any heat flow to happen. That's zeroth law of thermodynamics. The next one, what we have to learn is first law of thermodynamics. That's very fundamental. First law states regarding conservation of energy, not regarding thermal equilibrium. How that thermal equilibrium has been attained, that is explained. Delta Q is equal to delta U plus delta W. When some amount of heat delta Q is added to a gas, that amount of heat energy may be either used for increasing internal energy, maybe or used for doing an external work, all these things. If delta Q is positive, that is heat is added to the gas, delta Q is positive. If delta Q is negative, heat is rejected by the gas. And if delta U is positive, internal energy increases. And if delta U is negative, internal energy decreases. One more convention for work done. If delta W positive, expansion, gas expands by itself. Gas expands, work done is positive, volume increases. So when gas expands, work done is positive. When gas gets compressed, volume becomes, change becomes negative. So W becomes negative. So if heat is transferred from surroundings to system, heat is absorbed by the gas, heat transferred to the gas. All these cases, delta Q is positive. When temperature increases, internal energy change is positive. When temperature decreases, the internal energy change delta U is negative. U stands for internal energy. Delta U stands for change in internal energy. Internal energy refers to sum total of kinetic and potential energies of all the molecules of a substance, but for ideal gas. Internal energy referred to as average kinetic energy of molecules in a frame in which center of mass of that system is at rest. That means we should be situated in a frame which is called center of mass frame. You choose the center of mass of that gaseous system. You have to stick on to that center of mass and you have to measure the kinetic energy of all those molecules. So average kinetic energy in center of mass frame is referred to as internal energy. How to measure this quantity delta Q? As in a quick revision class, we can directly enter into that equations and all. Delta Q is equal to, in last chapter also we have discussed formula for delta Q. So number of moles into specific heat at constant pressure into delta T. What is delta U formula? Number of moles mu CV delta T, where delta U by delta Q refers towards CV divided by Cp. CV by Cp is 1 by gamma. Gamma is the ratio of specific heats. Okay. And gamma for monatomic gas. Gamma monatomic gas is 5 by 3. That is 1.67. Gamma diatomic, that becomes 7 by 5. That is 1.4. So as the atomicity increases, gamma decreases. Gamma stands for adiabatic index or ratio of specific heats. Cp by Cv, adiabatic index. Okay, index of adiabatic process. So delta U by delta Q is 1 by gamma. And also connecting these together. For a monatomic gas, gamma is 5 by 3 means 1 by gamma is 3 by 5. That means if 5 joule of heat is added to the gas, that may be used for 3 joule. Among that 3 joule is used for changing internal energy. Delta U is Cv. So that is 3 joule and the rest of the 2 joule is used for performing the work. So what is 1 by gamma really? 1 by gamma is the amount of fraction of heat which is used for changing internal energy. Delta Q is the amount of heat energy supplied to the gas. Delta U is the change in internal energy. So what fraction of the supplied heat is used as change in internal energy? That is referred to as 1 by gamma. And if delta Q is 5, delta U is 3 and delta W is 2. That's the mathematics. For diatomic gas, this 5 will be replaced by 7, 3 will be replaced by 5 and W is replaced by same 2, it will be repeating. Okay, this is the thing. What is the physical significance of this gamma? In many problems we can make use of it. Last year also advanced paper in physics, a question was asked from this concept and we could have been answered it so quickly if you were knowing about this. So first law of thermodynamics, delta Q equal to delta U plus delta W. Formula for delta Q, formula for delta U, by heart it, delta U by delta Q is 1 by gamma. Okay, so that's something about first law of thermodynamics. And what is delta W? Delta W is equal to P delta V. Okay, that's the formula for general formula for doing finding the work done in thermodynamics. That is delta W equal to P delta V. That's first law. Now let us discuss some of the thermodynamic processes. The first basic process is isothermal process. Isothermal process. We will discuss everything about isothermal process based on the previous papers. Isothermal process is that process in which temperature is a constant. Temperature is a constant. what all are the variables? Pressure and volume are variables. Temperature constant, pressure and volume are variables. As temperature is a constant, internal energy is a constant. So change in internal energy would be 0 for a gas. Because for a gas, the isothermal process, there won't be any change of state. Okay, normally at the temperatures what we are handling with. But in every process, it cannot be seen like that. For example, during melting or during boiling, temperature remains constant. But during that melting or boiling, delta U cannot be 0. So change in internal energy is not 0 during melting and boiling. But for a gas, ideal gas when you treat, or any gas, real gas or ideal gas, when the process is taking place at constant temperature, delta U would be 0. So delta U equal to 0, temperature constant, U constant. Then first law becomes delta Q equals delta W. So if any amount of heat added to the gas at constant temperature is completely utilized in expansion. So if delta Q is positive, delta W is positive, so gas expands. Any amount of heat given to a gas at constant temperature, that amount of heat is used for increasing volume. That's why it performs a positive work if expansion work is positive. Okay, that's very important. Variables are pressure and volume. How do they relate? PV equal to a constant, and that is the equation of state of isothermal process. That is P1 V1 equal to P2 V2. Then PV graph shape. PV graph is a rectangular hyperbola. P proportional 1 by V. So it obeys Boyle's law. The process obeys Boyle's law. Given mass of ideal gas at constant temperature, its pressure varies inversely with its volume. P1 V1 equal to P2 V2. So P1 by P2 is V2 by V1. Now, the slope of PV graph. Slope of PV graph is dP by dV. dP by dV happens to be minus P by V. dP by dV equal to minus P by V. That we have learned in the previous class also. dP by dV, regarding dP by dV, dP by pdV, we have learned. That was expansivity. We have learned that was expansivity, that was something different. Here it is dP by dV equal to minus P by V. That is the slope of PV graph for isothermal process underwent by ideal gas. Now, the work done during this process, work done during an isothermal process. Integral P dV, V initial to V final. This is the general formula for work done for any process. So here also we can use this. But P equal to PV equal to a constant. That is why P equal to constant divided by V. So integration of V1 to V2, a constant. What is that constant? Mu RT divided by V dV. On integrating and substituting the limits, you get mu RT log V2 divided by V1. Mu RT log V2 by V1, where work done is proportional to T log V2 by V1. And log V2 by V1 is called the expansion ratio logarithm. V2 by V1 is the expansion ratio. Log of the expansion ratio into mu RT. This can be rearranged as mu RT is P1 V1. So P1 V1 log V2 by V1 can be altered as P1 by P2. Like this you can make some changes in that equation. Okay. So work done is equal to mu RT log V2 by V1. When V2 greater than V1, work done is positive. So mu RT log V2 by V1. This part is very important. The next process is an adiabatic process. Adiabatic process. That's going to be another important one. Adiabatic process is that process where delta Q equal to 0. Then first law becomes delta U equal to minus delta W. What do you mean by that? entire change in internal energy is manifested as the negative of the work performed. That is why when gas expands, the delta W is positive, then delta U is negative. That means internal energy decreases when gas expands. That is why when a gas is expanding adiabatically, its temperature decreases. When a gas is expanding adiabatically, its temperature decreases. So ideal gas is expanding adiabatically. Expanding adiabatically, its temperature decreases. Adiabatic expansion causes cooling. Adiabatic compression causes heating. It's very important one. Delta U equal to minus delta W. Okay, let us choose the PV graph here. PV graph is also a hyperbola, as very much similar to that which was discussed earlier, which is an isothermal process. It's also similar one, but the slope is slightly greater. The slope of this graph, dP by dV, is equal to minus gamma times P by V, where gamma is the ratio of specific heats. So gamma is greater than 1. That's why the graph has more steepness. Adiabatic process, the change in pressure for given change in volume is larger. So for adiabatic process, for a given change in volume, the change in pressure is much larger than that of isothermal process. So by comparing isothermal process and adiabatic process, students, you don't forget this. For same changes in volume, change in pressure is much larger for adiabatic process in comparing with that of isothermal process. Okay. Isothermal process, for a given change in volume, all gases will have same changes in pressure. For example, when volume is halved isothermally, pressure is doubled. When volume is doubled isothermally, pressure is halved. But it's not so for adiabatic process. Adiabatic process, if it is adiabatic process, it depends on the nature of the gas also, atomicity, gamma. Okay, monatomic gas gamma is largest. That's why the slope is largest for monatomic. Larger slope of PV graph for adiabatic process is for monatomic gas. That's why the pressure change is also more for adiabatic process for monatomic gases. Okay. Now, work done during adiabatic process. The work performed. Work done is equal to mu R T1 minus T2 divided by gamma minus 1. Or mu R T1 can be P1 V1. Mu R T2 can be P2 V2. So P1 V1 minus P2 V2 divided by gamma minus 1. So these two formulae worth not touch. Here, variables are pressure, volume, as well as temperature. Three variables are there. So three equations of states are there. One of that is PV raised to gamma equal to a constant. Other one is PV raised to gamma minus 1 equal to constant. The third one is T raised to gamma, P raised to 1 minus gamma equal to constant. You can also try to write all this in various forms. In previous papers, comparison of a given equation with any one of the standard equation is frequently asked. Okay, so that is adiabatic process. Adiabatic process is commonly a Cuet process, but isothermal process is comparatively a slower process. A gas is undergoing adiabatic expansion means it is undergoing a sudden expansion. Okay, adiabatic process, adiabatic expansion and adiabatic compression. Equation of state, first law of thermodynamics, work done formula, PV graph, slope of PV graph. These many things are to be noted. The third one is isobaric process. Isobaric process is a constant pressure process where variables are volume and temperature. PV graph, when you draw PV graph, that would be a straight line like this. PV graph is a straight line. That is, pressure is equal to a constant process. Here, volume proportional to temperature, Charles' law. So VT graph is a straight line passing through origin. Draw VT graph here. Like this, you have VT graph for ideal gas, it should be passing through origin. Ideal gas, the graph should be passing through origin like this. Okay, whatever slope of it, it should pass through origin. So volume temperature graph. Expansion. When volume is proportional to temperature, if a graph is shown like this, it is sure that pressure is constant. So this is gas is expanding at constant pressure. When temperature doubled, volume is also doubled, irrespective of the nature of the gas. When temperature halved, volume is halved. Okay, the process is called isobaric process and it obeys Charles' law. This process obeys Charles' law. So what is the equation of state? V1 by V2 equals T1 by T2. V1 by V2 equals T1 by T2, or V1 by T1 equal to V2 by T2, or V proportional to T. V equal to a constant into T. Okay, pressure equal to constant. All these things are to be noted. First law can be written as it is. Delta Q equal to delta U plus delta W. That is, any amount of heat supplied to the system is used for changing internal energy and also for performing work. These are the two things to be noted. So delta Q equal to what? Delta U plus delta W. Okay. Any amount of heat supplied is used for two purposes: for changing internal energy and also performing work. Okay. These two terms will not cancel. Okay. The next one is an isocoric process. Isocoric process is a process where volume is a constant volume process. That is why work done is zero. So entire amount of heat supplied is used for increasing internal energy. Here volume constant, but variables are pressure and temperature. P proportional to T, Gay-Lussac's law. PT graph is a straight line inclined to temperature axis but passing through origin for ideal gas, provided T is in Kelvin. Temperature should be in Kelvin, not in degrees Celsius, for that graph to pass through origin. But straight line nature will not change even if it is mentioned in degrees Celsius. P proportional to T, P1 by P2 equals T1 by T2, that is isocoric process. Okay, work performed is zero, delta Q equal to delta U, volume is a constant. So very important thing is that work performed is zero. Okay, but when temperature is doubled, pressure is also doubled. The percentage change in temperature may be given. The same percentage change will happen in pressure also, because P proportional to T and obeys Gay-Lussac's law. Okay, getting all this data together, let us revise all this together by using two graphs. Okay, let me show that this graph is very, very, very important. You have all these processes drawn together for PV graph. And here first graph shows expansion, second graph shows compression. Let me draw two more here, two more. Okay, I am plotting this for same changes in volume, same changes in volume, same changes in volume, same changes in volume. See this? Same changes in volume. First one is expansion and second one is compression, as I said. Let us identify. The first process here, which is horizontal pressure constant, that is isobaric expansion. Isobaric expansion. But here it is isobaric compression. Isobaric compression. Okay, and the vertical process, that should be isocoric, and this is isocoric. Normally that no arrow marks give. Isocoric. Now we have to recognize isothermal and adiabatic. Students, can you recognize? The first picture, for same changes in volume, more change in pressure is noticed for adiabatic process. So the lower one is adiabatic, more steeper. And the above one, second hyperbola, upper hyperbola, is isothermal. Similarly, in the second case, here for same changes in volume, more changes for pressure is noticed for adiabatic. So the upper one is adiabatic and lower one is isothermal. That is to be noted. Maybe asked in exam. Okay, now observe same changes in volumes for all these processes in each. Okay, then we know each of these are called non-cyclic processes. Non-cyclic process, the system will not come back to the same initial thermodynamic state variables. Okay, if the system comes back to the same thermodynamic state variables like pressure, volume and temperature after a series of processes, then that is a cyclic process. Here each of these processes mentioned are not cyclic, non-cyclic processes. Okay, and work done from PV diagram we can find out as the area of that curve under that curve, area under the curve made with volume axis, area under the curve made with volume axis. So in which of these cases isobaric process least work in compression? See, during compression isobaric compression does least work. It is easiest to do isobaric compression work, but not so for expansion. Isobarically, ideal gas needs extra work to expand it. Ideal gas needs more work, extra work, additional work, maximum work during isobaric expansion, but minimum work during isobaric compression. Let us, we can compare isothermal as well as adiabatic processes. Isothermal process, you can see the area under the graph. Area under the graph is greater than that of adiabatic. That is work done isobaric greater than work done isothermal greater than work done adiabatic for expansion. But for compression, you see, but for compression, work done adiabatic greater work done isothermal greater work done isobaric. That is for compression. So while ideal gas is being compressed to same changes in volumes in each of these three processes, least work is performed during isobaric compression. Then maximum work is performed during adiabatic compression. See, whatever, in each of these cases, for a given change in volume, maximum pressure change happens in adiabatic process. Okay. For given change in volume, maximum pressure change happens in adiabatic process. Like this, these two graphs are very important. Children, you please note and by heart all these things very well. Okay, I have tried to explain maximum, okay, within this limited time. Now, there are many more processes to be discussed, particularly reversible process and irreversible processes. Reversible processes are those processes which are reversible in all senses. That means at every instant of the process going on in one direction, the process can be reduplicated. Exactly, it can be reproduced in the reverse direction. Okay, same changes can be produced in the reverse direction also, then that is called reversible, but no such processes. No processes are reversible. It is limited because if a process is to be reversible, that process should be quasi-static. A process to be reversible, that process should be quasi-static. Quasi-static means that should be extremely slow. Extremely slow. It should be slower than how a plant grows. You need not see, may not have seen how the plant grows. By looking, you cannot see. But that is an quasi-static process. Extremely slow. The second condition is non-dissipative. Non-dissipative. So the process should be non-dissipative, then only it is reversible. A process to be reversible, it should be quasi-static as well as non-dissipative. No, there should not be any energy loss. No processes satisfying these two conditions. That is why no processes are reversible. But in theory, in many occasions, we used to prefer reversible processes in many occasions. Okay. Then next one is irreversible process. Irreversible processes are the general processes of nature. You may have heard about reversible processes in chemistry, that is chemically reversible or chemically irreversible processes, that is not thermodynamically reversible or irreversible processes. Thermodynamically reversible processes are never possible, only theoretical. Okay. Now cyclic and non-cyclic processes. If a process is cyclic, we can easily draw the PV graph. The process is cyclic, a cyclic process, then it would be shown like this. Okay, PV graph, it represents cyclic process. The work performed during a cyclic process, you can easily find out the area of the closed loop. Area of the closed loop gives work done. And if volume max is horizontal and this sign direction is clockwise, work is positive. If delta W is positive, volume max is horizontal, clockwise. Clear? So cyclic process clockwise, sense of arrow mark. Volume max is horizontal, W positive. But if volume max comes at the vertical axis and pressure comes here, clockwise means delta W is negative. Okay. Another better way to learn it. If that expansion part of the curve comes above, then work is positive. Here compression curve, compression part, arrow mark, leftward arrow mark is below. So that area under that graph is less. That's why work is positive. Okay, expansion curve comes above, work is positive. Compression curve comes above, work is negative. Okay, that's about PV graph. Okay, now we'll be moving to heat engines and Carnot engines. We have discussed different thermodynamic processes. Now heat engine and Carnot engine. Heat engine. Heat engine is the device used for converting heat into mechanical work. Heat is the input and work is the output. A schematic picture of the same can be of this form, like this. It consists of mainly a working substance, maybe some gas, working substance which extracts heat Q1 from a high temperature reservoir called source and rejects a heat Q2 to a low temperature reservoir temperature T2 called sink. The difference is performed as work. That is W, and W can be measured as Q1 minus Q2. Then the efficiency of heat engine is the output, useful work output, useful power output, that is W, divided by input heat. Input heat is Q1. So eta equal to W divided by Q1. So eta is equal to Q1 minus Q2 divided by Q1. So eta is equal to 1 minus Q2 by Q1. That is the formula for efficiency. So efficiency of heat engine is eta is equal to 1 minus Q2 divided by Q1. Q1 minus Q2 by Q1. Eta is W by Q1. All this you by heart. Heat Q1 is extracted from a high temperature reservoir. Working substance absorbs that heat and does the necessary works. Rest of the work is converted into the heat Q2. So Q1 is greater than Q2 and Q1 minus Q2 is positive, and that is work W. This is a general illustration of heat engine. Okay. Now, how this heat engine can be converted to a Carnot engine? For converting that heat engine into a Carnot engine, this processes where the working substance absorbs heat, rejects heat, all these processes should be reversible, for which a reversible adiabatic and reversible isothermal processes are chosen. 4 processes have been chosen so far for Carnot processes. If you go for the PV graph here, you can show the PV graph like this. And starting from here, pressure P1, volume V1, temperature T1, to pressure P2, volume V2, temperature T1, expansion isothermally. So that process 1 to 2 is isothermal expansion. isothermal expansion. Isothermal expansion. So P1 V1 T1 to P2 V2 T1 isothermal expansion. What is the equation of state? P1 V1 equals P2 V2. What is the work performed? W1 is equal to heat transferred. In that process, isothermal as delta U is equal to 0. No change in internal energy. So entire work is converted into heat. Work is positive, so heat transfer is also positive. So heat is absorbed during that process. That absorbed heat is equal to the work performed. That is equal to mu R T1 log V2 divided by V1. Delta U is equal to 0. That is isothermal expansion. Equation of state P1 V1 is equal to P2 V2. The next process is P2 V2 T1 to P3 V3 T2. That process is a sudden process. That is an adiabatic process. That is a hyperbola. Hyperbola should be a hyperbola. And that temperature T2 is going to be less than T1 because that is adiabatically expanding. Adiabatic expansion causes cooling. So the process 2 to 3 is an adiabatic expansion where the equation of state is P2 V2 raised to gamma equal to P3 V3 raised to gamma, or you can also choose T1 V2 raised to gamma minus 1 equal to T2 V3 raised to gamma minus 1. Okay, any one of these equation of states can be chosen. The work performed during that process mu R by gamma minus 1 into T1 minus T2. T1 is the temperature of source and T2 is that of sink. Okay, during that process cooling is resulted, no heat transfer, Q equal to 0. Okay, so Q is equal to 0 during that process, no heat transfer process. Okay, next process is 3 to 4. First one 1 to 2, second one 2 to 3, third one 3 to 4. 3 to 4, where to where? P4, V4 and T2. That is an isothermal compression. Isothermal compression. What is the work performed? W equal to mu R T2 log V3 divided by V4, where V3 by V4 is the expansion ratio. T2 is the temperature of the sink. And that work is negative. First work 1 to 2 work done positive. 2 to 3 work done is positive. So 3 to 4 work done is negative. But during this process work done is negative. That's why heat is rejected. Rejected heat is Q2. So absorbed heat is Q1. Rejected heat is Q2. Okay, equation of state is P3 V3 equal to P4 V4. Temperature constant, energy change 0. Last process 4 to 1. 4 to 1 is adiabatic compression. There is no heat transfer during that process. 4 to 1 work done is equal to mu R divided by gamma minus 1 into T1 minus T2. Okay, equation of state is T2 V4 raised to gamma minus 1 equal to T1 V1 raised to gamma minus 1. Any one of those equation of states can be mentioned as it is also. You can follow the same method there. Okay, so what is the total amount of heat transfer, net heat transfer during this entire process? Net heat transfer Q is equal to Q1 minus Q2. Q net. What is Q1? Q1 is equal to W1. That is mu R T1 log V2 by V1 minus what is Q2? Mu R T2 log V3 divided by V4. Okay. Is it clear? Why minus sign has come here? Because Q1 is positive, absorbed, Q2 is negative, rejected. That is why this minus sign I have already chosen here. Okay, but from the equations of states, you can take the ratio of these two equations of states. From that, you can easily say that V3 by V4 is equal to V2 by V1. That result is also important. That may be also asked. So V3 by V4 can be V2 divided by V1. So what is the net heat transfer? Q net is equal to mu R log V2 by V1 into T1 minus T2. Then total work done. What is the total work done? Total work done is equal to Q net, because W equal to Q1 minus Q2. Same is the work done. So Q net is equal to W. Why Q net is equal to W? Because this total process, some of the processes is happening to be a cyclic process. In cyclic process, delta U is 0. So delta Q equal to delta W. So net work is equal to net heat. Then efficiency eta is equal to W divided by Q1. It is not net Q. W divided by Q1, it is not W by Q net. Then W by Q1 is what? W is mu R log V2 by V1 into T1 minus T2 divided by, what was Q1? Q1 was mu R T1 log, what is that? V2 divided by V1. So mu R cancels, log V2 by V1 cancels, so efficiency becomes T1 minus T2 divided by T1. So that result is very important. So that steps involved also important. That is why I have shown it. Once again, you may have learned it already. Then efficiency equal to 1 minus T2 divided by T1. You may seem this to be faster, but you can see it. Pausing, you can see this. Okay, then no problem. You can understand. Efficiency equal to 1 minus T2 by T1. But the formula for efficiency of heat engine was 1 minus Q2 by Q1. Efficiency of Carnot engine is 1 minus T2 by T1. From this we can easily conclude Q2 by Q1 is equal to T2 by T1. But T1 and T2 should be in Kelvin scale. Last year 2023 and 2022 mains papers, these questions were asked. Many questions I have seen that Q1 and Q2, T1 are given, T2 is asked, or any one of the variables, only missing the other three are given, the missing variable was asked. So this formula is very important. Okay, Carnot engine efficiency formula is very important. 1 minus T2 by T1. T2, if T2 is equal to 0 Kelvin, efficiency becomes 1. That is never possible because 0 Kelvin temperature is unattainable. So efficiency of that engine, maximum efficiency cannot be available. So efficiency will be less than 1. So efficiency is less than 100%. But for a heat engine, this Q2 can be 0. But even when Q2 0, T2 cannot be 0. So maximum efficiency can be 100%. Okay, maximum efficiency as per theory itself. Okay, theoretically also even this 0 Kelvin is unattainable. So a maximum efficiency, but never practically one, that is limited, and that is the statement of second law of thermodynamics. No process is possible whose sole result is the complete conversion of work, extracted heat into useful work. No process is possible whose sole result is the absorption of heat from a hot reservoir and complete conversion of it into mechanical work. That is never possible. It's a negative result. Okay, that is called second law of thermodynamics. Okay, Carnot engine is an ideal reversible heat engine which works on two temperatures T1 and T2. The working substance of Carnot engine should be ideal gas. Okay, no engines can be efficient than Carnot engine whose operating temperatures are T1 and T2. T1 is greater than T2. Now, thermal capacity of the source and sink are to be much larger, so that any amount of heat added or removed will not make any change in the amount of heat content and will not make any the temperature of that source and sink. Now, one more topic is left, that is called refrigerator. Refrigerator is the reverse of heat engine. Refrigerator is the reverse of heat engine. The process happening in refrigerator is the reverse process of heat engine. Okay, then the schematic diagram needs to be reconstructed like this. Like this. If you have amount of heat extracted at the cold reservoir is Q2, rejected at the hot reservoir is Q1, then W is the work performed. See, everything reversed. Here heat T1, higher temperature reservoir, T2, low temperature reservoir. This time, heat energy is absorbed by the working substance at a lower temperature and heat energy rejected at the higher temperature. That wordings are very important. While we are reading the question paper, we may not be, if we are not aware of all this theory, you may not understand which one is given, because W, Q1 and Q2, all the three are being given in same system of unit, maybe joule, calorie or power, watt. Okay, maybe in watt also in question papers. So once again, Q2 is the amount of heat energy absorbed at the cold reservoir by the working substance. Q1 is the amount of heat rejected at the higher temperature source by the working substance. But rest of the equations almost same. W equal to Q1 minus Q2 doesn't find any difference. But here the difference is that we do not think about efficiency but performance coefficient, COP. Coefficient of performance alpha is equal to output by input. Here output is which? W, Q1 or Q2 is output. The cold reservoir is the output. Temperature of the cold reservoir should be less. So more amount of heat should be extracted from the cold reservoir. Then only cold reservoir keeps on cooling. So Q2 is the output. Output is not W. W is the input. So Q2 by W is the performance coefficient and alpha equal to Q2 by W, that is Q2 by Q1 minus Q2. If you think this refrigerator as a Carnot refrigerator, making all the processes reversible, the performance coefficient alpha can be written as T2 divided by T1 minus T2. So alpha is equal to T2 by T1 minus T2. Alpha stands for performance coefficient. Now, if Q1 is equal to Q2, alpha becomes infinity. Q1 is equal to Q2 means what? Entire amount of heat extracted is converted into Q1. So W is equal to 0. W is equal to 0. It is never possible to work a refrigerator without electricity, without external agency. That's why work done cannot be 0. Q1 cannot be equal to Q2. So efficiency cannot be infinity. There is again a negative statement. The performance coefficient of refrigerator cannot be infinity. So performance coefficient, the COP of a refrigerator is less than infinity. So that is the second law of thermodynamics. No process is possible whose sole result is the transfer of heat from a cold reservoir to a hot reservoir in the absence of external heat. Repeating, no process is possible whose sole result is the transfer of heat from a cold reservoir into a hot reservoir in the absence of external agency. Okay, that is the second law of thermodynamics statements. Okay, we have learned heat engine, Carnot engine, as well as refrigerator, Carnot refrigerator also. Okay, now the connection between performance coefficient of a refrigerator and efficiency of a heat engine. What is the connection? What is the relation between eta and alpha? Eta is equal to 1 minus T2 divided by T1. That is why T2 by T1 can be written as, what is T2 by T1? 1 minus eta. So what is T1 by T2? That is 1 by 1 minus eta. All these conversions are very important for you during examinations. Okay, you have to be so flexible with all these variations in the results. Results you can produce in varying ways. Now, performance coefficient alpha equal to what? Performance coefficient alpha T2 Q2 by W. Q2 divided by W. You can remember that here it is written T2 by T1 minus T2. T2 by T1 minus T2. You can take the reciprocal 1 by alpha equal to T1 minus T2 by T2. That is 1 by alpha equal to T1 by T2 minus 1. This T1 by T2 you can substitute there. That is 1 by alpha equal to 1 by 1 minus eta minus 1. You can rearrange. That is 1 by alpha equal to 1. Denominator common 1 minus eta. Then here comes minus 1. Here comes plus eta. That is 1 by alpha equal to eta divided by 1 minus eta. So alpha equal to 1 minus eta divided by eta. Alpha is 1 minus eta by eta. For example, if eta is equal to 0.9, eta less than 1, alpha is equal to 1 minus 0.9 divided by 0.9, that is 1 minus 0.9 is 0.1 divided by 0.9 is 1 by 9. So performance coefficient is 1 by 9. Alpha is equal to 1 minus eta divided by eta. From this you can also write alpha eta equal to 1 minus eta. Alpha eta is equal to 1 minus eta. All these results are very important. Divide throughout by eta. That is alpha is equal to 1 by eta minus 1. Alpha is equal to 1 by eta minus 1. This result is also important. That is 1 by eta is equal to 1 plus alpha. 1 by eta equal to 1 plus alpha. So eta equal to 1 by 1 plus alpha. If alpha equal to 1 by 9, eta you can find out 1 by 1 plus 1 by 9. That is 1 by, you will get 10 by 9. That is 9 by 10. That is 0.9. If alpha, eta is equal to 0.9, alpha is 1 by 9. You can also compute vice versa. So these relationships are also worth noted. Okay, with that we have completed almost all the topics I have discussed very well as a part of a quick revision of chapter Thermodynamics. We will be seeing with the next chapter soon. After this we will be following with chapter Kinetic Theory. Thank you very much.